a big thanks to the chairman for the nice introduction. And so my name is Jun Jiang. I'm from China, but my Swedish friends always call me Yun Yang because that's how Swedish to pronounce the J word. Yeah, I actually did my PhD in KTH 20 years ago. So my friends asked my friends call me JJ to make it easier. Double J. Yeah. So it's a big pity that I cannot go to Uppsala directly because of some very special case. Yeah. You can understand how pitiful I am to not be able to join this nice conference. Okay, so today please allow me to introduce our recent work about a robotic AI chemist. We all know that the chemistry started from AI chem. Yeah. Newton is, of course, a successful physicist, but unfortunately, he is not a good chemist because he actually have spent a lot of energy and efforts to try to convert some non-noble metal into gold. Of course, he failed. Yeah. The only problem is because, he has no theoretic guidance, has no physical rules to tell him that that's not impossible. On the other hand, we believe that Edison is a successful chemist because after long years try and error, he finally found this good material as a barbed wire. Yeah. But his method or his paradigm is called try and error. That's why some people call that our chemistry as chem is try. So this is kind of awkward. Yeah. But actually we do have the physics rules or the principle to guide our theoretical design or guide our material design. That's called quantum mechanics theory, right? And it is because a lot of data connection from spectroscopy that people finally found that build this quantum mechanics rule. So following this track, I have did my PhD study as a theoretical chemistry in the theoretical chemistry department of KTH, and I got my PhD diploma in 2006. And following this track, we try to do some good design based on first principle rules, and sometimes we get good publications, and I get proud of our work. But one day, my wife had enough with me. She started to laugh at me. She said, "So you have so many inventions. Then when will we get rich? Please show me some money." So suddenly I became speechless. This is actually a sad story. Although we can do a lot of good design from the theory, but there's a huge gap between the first principles rules and the real world. So the real practice cannot be fully guided by theory. Why? Actually, Dirac has already told us the reason. He said the exact application of these laws leads to equations much too complicated to be solvable. So our first principle rules are quite clear and elegant, but our chemistry world is actually very dirty. It is a high complexity real world. So if we try to clean up this pyramid, there's a curse of dimensionality, high dimensionality problem, and also there's a limitation of computation power. That's why we recently tried this data-driven AI mode, like we all have done in people in this conference. The first problem is, can we really build useful AI model upon scientific data? The first question is, do we really have enough high-dimensional big data in science? The answer is unfortunately no. We can follow the methodology of Einstein, that we can do a lot of calculations based on a theoretical rule, but they are in principle low-dimensional data. They are based on ideal approximation. On the other hand, we can follow the Heisenberg's rule. We can go with experimental characterization, but those are too expensive. Yeah, we all know how expensive it is to do a real experiment. Yeah, I have actually talked to my friend who is doing experimental chemistry. They always said, okay, we have spent years to collect like 100 set of data, which is of course not enough for machine learning training. Now we recently try to find another solution. It's called use a machine to produce and also to utilize high quality data. We believe this is actually a new way. Firstly, we can build a pre-trained machine learning model with big data from theory. Then we apply transfer learning to upgrade our model with small data in experiments. This is actually new because I actually have collaborated with many experimentists almost every time. If we met a problem to explain the results, we cannot change our model because our model is based on the low dimension equation, like Schrodinger equation. You are not able to change the equation. You cannot change the model. But now, if we put this theoretical data into a neural network, that's actually adjustable, changeable. So we can use experiment data to upgrade our model now. Then this model, so-called model to fuse this theory and experiment data could and is possible to guide the complex system studies. That's what we are doing now. Try to build a robotic AI-chemist system or even a lab in our University of Science and Technology of China, USDC. First, we have developed this machine reading system. It's actually based on the natural language processing techniques to NLP techniques to read the paper and extract a large number of data. Then we have this machine sync system, which is the typical supercluster to do the theoretical simulations. But you know that when we were doing theoretical simulations, it is actually like the machine is thinking in the physics rule. Of course, we need to do the practice because the experiment is always right, always correct. So we introduce this robot to do the full life cycle experiment and collect all the data, precise data. We all know that in man-made data, you always have some deviation, but the robotic data could be very precise and at least very reproducible. Yeah. So Wei Shang and Fei Zhang, they are two professors from the automatic machine department in our school. So with their help, we build this system and put them together with web-based software. It's like an operating system. It was developed by Hen Yuxiao and Qin Zhu. Now we have this web page, which is actually accessible from everywhere from the internet. So when you log in, you are able to see that many robotic devices, not only the mobile robots, but also some other chemical workstation, which have been converted into something can be complicated with robots. Yeah. Then you can drive the experiments and they can collect the full life cycle data. Yeah. And you can see that now we can see the error bar for the robotic experiment, which is very narrow, comparing to human experiments, which is wide in this error bar. So you understand robotic experiments do have some advantages. And at the same time, it is very easy to collect the full life cycle data. You know, before that, I have spent 2 years to do the experiments. So we all understand it is very difficult to write down all of those experiment conditions. But now it is easy, yeah, with this software. Oh, I lost one page here. Let me try to show you. Okay, so it's fine, yeah. Anyway, so now we have converted the operation of experiment into a flow chart you only need to put different, different workstation together, draw a draft. Then the operating system will decode this draft and then call the machine to do the work. And this is a demonstration of our first work. Yeah. So we have applied the machine reading system to digest like 16,000 paper in the OER field, oxygen evolution reaction catalyst field. Then it proposed that we may use these 5 elements, putting them together. So after the documentation, we still have to done like 500,000 possible combinations to be able to get the best formula. If I'm stupid enough to do all of these experiments, it could take me like 1,000 years. Of course, we should do it in a smart way. Now here we conducted like 25,000 theoretic simulations. So then we build a pre-trained model with machine learning. Now we asked the robot to conduct the experiment for 200 times. Use this experiment data. We calibrate the theoretical model. We do the transfer learning. Then this model is able to fuse its theoretical and experiment data and guide us to do the Bayesian optimization, and we get the best formula in almost immediately. The whole work has been done in 5 weeks, so it's quite efficient and also elegant. Yeah, we can see the advantage from this page. If we only use this experiment data to do the analysis, we can see this is a serious overfitting problem. We are able to explain all the points, but they are not transferable, because here you have to pay respect to each data point. You are not able to wash out or clean any data, because they are all equally important. If we apply theoretical model to explain the experiments, we have this underfitting problem. That's typical because of the gap between theory and the experiment. And so if we use experiment data to calibrate or to retrain our theoretical theory-based prediction model, we now have a good model to explain the results, and also transferable to explain or to predict other system. So here we found the global optimum for this OER catalysis, high entropy catalysis. So after that, we move forward to do some realistic work, not only to demonstrate. So recently we have done work using the Martian meteorites, which is a job from the Deep Space Lab in the NASA department of China. So they asked us to see if we are able to create useful chemicals with unknown materials and unknown environments based on almost unknown rules. This is a big challenge, but very useful, because they said we are not able to send tons of chemicals from Earth to the Moon or to the Mars. The reasonable way or the smart way is to try to use the local resource on Mars, but you are not able to send the scientists to there. So if we are able to send the robot there, the robot can connect the Martian ores and then make usable chemicals. So we have done the work. Yeah. So firstly, we use Leap's spectrum to empower the robot to analyze the metal elements in the meteorites. After that, we are able to build this theoretical model, because you will understand the metal elements there. Then at the same time, the robot conduct all of these experiments to connect the necessary, the material, and then make the catalyst and test the performance. Then the data was used to calibrate the theoretical model. And then we screen all of these 3 million combinations very quickly. And we produced a good formula. And now it is able to produce oxygen now. Yeah. So after the publication, the lecture magazine is quite happy about this work. They actually write highlights in their website, and also deliberately made a video to broadcast this paper. Yeah, and but we like the comments from Andy Cooper at Newport University. He said this is quite useful for and could be applied broadly to all kinds of chemistry. Yeah, we like this idea very much. That's what we are doing now. Firstly, we are trying to make a useful catalyst for the for the has reading like 50,000 paper and propose the elements, and then Professor Cao select the right combinations based on the analysis, and we conducted 18,000 simulations and 300 experiments to build a useful model, and it guide us to schooling this almost 2 million formula. And now the produced oil very has the highest performance, but also has the best stability, yeah, ever. And I also collaborated with Newport, Andy Cooper in Newport for finding a high entropy letter I9. We follow the same track, yeah. The useful part is first we do the Bayesian optimization with pure experiments from the robot. But if we combine theoretical large big data and small data from the robotic experiments, we find a good solution. And also, Professor Zhu has used our platform to make this useful result, has produced these useful nanocrystals. And now we are trying to invite more scientists to use our platform, because this platform is now like a play and plug system. Every time we have new experiments, the scientist only need to donate his device into our lab. Then we and robot we write some code to all this new device. Then we can do the experiments. Yeah. So we are moving forward to go for prototype. Yeah. It likes the big scale chemical robotics system going on in our system. And Andy Cooper actually appreciate our development in introducing the computation brain, because in his famous work at the lecture, he said our robot is very efficient, 100 times faster than a human, but our Bayesian optimization is blind because the lack of computation brain. Here, they cannot capture chemistry knowledge of physical model. System is able to, cover theory and also experiments because of this operating system. And there's a fast-growing community in this field, yeah. And many universities like Toronto University and Canada, and also Netherlands, Switzerland, ETH and EPFL, they all, also especially in Newport and Glasgow, they put big money to introduce big scale robots and large model, big model nowadays is very powerful, and to do this kind of research. And here in China, we also build an alliance, of AI scientists ecosystem. Yeah. Now we are trying to make some chemical training platform in different universities or even in some companies. Yeah. Connect different scientists to use the standard robotic work. Yeah. So standard robotic work is another advantages, because we all know that experimental results from different groups could be very different. Sometimes we work on the same system, but because of the different operation, different people, and the different device, we may have different experimental data. Now, if we apply the same robotic system at three cities, Hefei, Suzhou, and Zhengzhou, three cities are far from each other, but we send the command and they can make exactly the same chemicals and see almost the same identical evolution for the chemistry systems. To compare data from different labs, from different countries, which is important for us to build the necessary big data for AI training. So we believe that we are actually move forward to a data and model-driven paradigm. First, we will know we have this trial paradigm, but you can only find the local optimum because the huge resource required to finish all the experiments. We can also try with computational paradigm, but does not get big deviation from the reality. Here we are actually doing it like an active learning. First, you build the theoretical model by pre-training. Then you can use the pre-trained model to tell the robots to do the smart experiment, not all the experiments, but you can do the smart sample. Take the necessary sample to calibrate the pre-trained model with small data. Then you reach a real global optimum. That's the key. So this way, first the people, human scientists, define a question, define a need, then you can apply for robotic computing time, not computation time. Apply the AI model to recommend the substance and the synthesis route for computer interaction system, a web page system. You decide the research plan. Then the system will assign the robotic computing time for you. Not only the supercluster computation time, but also the robotic experimental time. We believe this could be another kind of computing, robotic computing. Then use this data to retrain, and you do a self-consistent, training until you reach a converged result. Then you actually have a new model, and this new model help you to make the necessary chemicals and the materials to meet people's needs. Yeah. At the same time, this model can be deposited into a cloud system. So in the future, maybe we can share a lot of and both experiments. Actually, we are trying to do this now. We are apply this by the between our Leo is our robotic AI-Chemist. Yeah, his Chinese name is Xiaolai. For the future means future. But his legal name is Leo. Yeah, English name Leo. So you can see, he asked ChatGPT to find a good OER catalysis. ChatGPT recommend this morph system, and actually tell Leo how to make it, how to synthesize it, the synthesis route, and workstations to do that. And if Leo told him that the result is not good, could you please improve the results? GPT can actually recommend, give us some suggestions. The first advice is quite good to optimize the meta ratios. So that's what Leo is doing now. Following ChatGPT's recommendation. Then again, Leo told GPT the results you proposed was not very good. Then GPT has done very surprising, can actually optimization code by itself. GPT, it writes the optimization code by itself and use this data to do the optimization and propose, this ratio for the metal elements. And performance was greatly, it's so smart, but not as smart as a human scientist because this optimization prediction is robust, not because a different for each in every estimation. So after 12 times, you see only 5 out of 12 proposals are much better than the previous experiments. So the successful rate is So it means that based on pure experiment data is not enough, like what Andy Cooper just said in his work. That's why we are moving forward to use ChatGPT or other big model to incorporate both theoretical model data and experiment data. So equivalent robots with more spherical-based perceptions, and also we are go forward for big scale lab, like in large space, and we will have different types of robots. Some will fly from the sky, some will be operating on the table, and some move forward. And in the future, I believe that we might change the way for the chemistry scientists to work. You can sit in the room, sit in the coffee house. You are working like a theoretical chemist. You just send a command, send your leads, and then the robot will do the experiments, will go collect the necessary samples, use the experiments, and then, of course, at the same time, do the simulations, put it together, and to meet what you need. That's our dream. And I hope you all may, you support us in this way. That's all. Thank you a lot. And appreciate your attention. Thank you.
Impressive. Any questions?
Thank you.
To the talk? There is one here.
Hey Jun, Paulo is here. Very nice talk.
Hi. Thank you.
I have a question. So all these language models, they change all the time. So then your procedures. So sometimes there are even examples that models after a couple of months become worse for some mathematical tasks. How do you want to make sure that your AI chemist is stable in the long run?
That's a very good question. And my answer is always we need to have human to supervise the system. The language models change all the time. They give different predictions when you ask the same question at a different time. But it is a human to choose the right decision, to decide research plan. And after it has produced some data, these are stable because the robotic lab and also the simulation, they are all based on physics rules.
All right, thank you very much.
Thank you. Thank you.
Okay, thank you.
Yeah, that's the key. Yeah.
Sorry?
Thank you. Thank you.
Okay, there is no more questions, so we go to the